Hello and welcome. This is a short video about the use of the system Ontop-spatial, a GeoSPARQL extension of the well-known system Ontop. Ontop performs on-the-fly SPARQL-to-SQL translation, so Ontop-spatial supports GeoSPARQL-to-SQL translation. So in this video we will show the use of Ontop-spatial in two use cases, the land management service and the crisis mapping service. In the land management service, our aim is to identify agricultural fields that violate protected areas in Germany. So we have different shapefiles describing various categories of protected areas and also shapefiles about fields. We have imported all shapefiles to a PostGIS database so that every shapefile corresponds to a different table in our database. So here we have several tables, one per shapefile. Most of them describe different kinds of protected areas, and we also have OpenStreetMap data and data about fields. So for example, this table corresponds to data about biotopes, and as you can see here, we have geometry columns where you can see the geometries of biotop areas in well-known binary format. Now we have to connect Ontop-spatial with this database. We can either select the web interface of Ontop that is based on Sesame Workbench or Protégé. Now we will use Protégé for the land management use case. As the default version of Ontop, Ontop-spatial can also be used from inside Protégé as a plugin. So here I have loaded the ontology of the land management use case, which is an extension of the GeoSPARQL ontology. As you can see here, we have the GeoSPARQL ontology imported, and this is the class hierarchy of our ontology, and you can see the different kinds of protected areas in different classes, as well as a class about fields. Now we can use the separate dedicated tabs for Ontop. First, we have the data source manager, where we have created a data source, and we have details about how Ontop-spatial can be connected to our database. So we provide credentials and the connection URL as well as the driver. Now we have a PostGIS database, and we can test the connection that is okay. And then we can proceed with the mapping. So opening Mapping Manager, we can see the mappings that accompany this ontology. So the format of the mappings is the OBDA native format that Ontop supports, and you can see how relational data are mapped to virtual RDF triples. For example, here you can see that the geometries that we saw before in well-known binary format are mapped to geometries of the standard GeoSPARQL literal data type. So here, using the mapping manager, we can create, remove, or edit mappings. And using the Ontop-spatial interface of the Ontop plugin for Protégé, we are ready to pose GeoSPARQL queries as well as save them. Now, first we can see a query where we want to retrieve agricultural fields that violate protected areas. So that this means that their geometry intersects with the one of protected areas, and we also need that a specific measurement should be below 0 in our results. So this is the query that we have posed, and this query will be internally translated into the respective SQL query, and it will be evaluated eventually in our PostGIS database. So we execute the query and we can see the results returned as RDF terms. And here you can see the geometry that follows the standard GeoSPARQL vocabulary and is exported in well-known text GeoSPARQL literal. So looking again at the query, we can say that we're using a spatial filter that's actually spatial join because we want to retrieve fields that intersect with protected areas. And we're using the GeoSPARQL function SF intersects inside the filter to express this spatial relation. So another way that we could use to pose this query would be this one that is more user-friendly. You can notice that we don't have a spatial filter anymore and no triple patterns regarding retrieving the geometries of fields and other areas, but instead we have a simple spatial predicate in a triple pattern that simply expresses the intersection as before. So this query is more user-friendly, but internally it is transformed to its quantitative counterpart, the query that we showed before, and it is again executed. So now we can move to the second use case that we have, the crisis mapping use case. In this use case, we have data about floods. We have the flood database. The data are originally stored in a PostGIS database, but they consist of a simple table, and it contains only basic information about floods, like the location and the type of floods, the date, and very little information about the location, like the city and country, but not even the official names of the cities and countries. So we would like to correlate this information with open data. For example, we have imported the Global Administrative Geography dataset that contains information about different kinds of administrative divisions worldwide. And we also have imported core inland cover information. The core inland cover dataset contains information about the land cover of different European areas. So we focus to the codes that correspond to water bodies that make more sense in our setting. And we also have imported OpenStreetMaps datasets about points of interest, always some categories like buildings, natural places, points and roads, as well as waterways. So in the same way as before, we imported the additional open data as shapefiles into our original database that contains data about floods in separate tables, as you can see here. And again, we want to create an Ontop repository in order to be able to query the data as if they were RDF data. So this time I'm going to use the web interface of Ontop that is based on Sesame Workbench. So I have already created a repository about floods. And I have some queries. So let's see, an interesting query combining information about floods and the different administrative divisions that the floods occur. This is a geospatial query that retrieves results of floods that whose geometries intersect with the geometries of different levels of administrative divisions. The total database is around 12 gigabytes. So here we can see the floods, the information about the location of floods that we have from our original dataset in the first two columns, and the most accurate information that we have about the divisions in the rest of the columns provided by the Global Administrative Division dataset. So moving on, we can see another query that also combines floods with a dataset from core inlet cover, and we want to retrieve floods whose geometries intersect with geometries of water courses according to the core inlet cover dataset. So we execute this query as well. And here we can see actually flooded water courses and the type of the floods. And last, we want to pose a query in order to retrieve the buildings that are affected by floods. So we pose another GeoSPARQL query retrieving buildings whose geometry intersect with the geometries of floods and the city and the country of these buildings. So we actually want to retrieve flooded buildings. So here is the name of the building and the type of the flood and the category of the building. There are supermarkets, museums, churches, place of worship, and so on. So that was it. You can download Ontop and Ontop-spatial from the links given in the description of this video, as well as more information about the use cases. Thank you very much for watching.